balancing chemical equations as presented by the Kenyan teacher. In this video, we discuss 4 things. Firstly, we are going to take you through the meaning of a chemical equation. Secondly, we shall look at components of the same. Thirdly, we are going to take you through how to count the number of atoms of different elements that make up a compound. And finally, we shall balance chemical equations, beginning with the meaning of balancing a chemical equation, and then we shall go through 4 examples of the same. Welcome and stay tuned till the end. So let's start off with the meaning and components of a chemical equation. So a chemical equation is a symbolic representation of a chemical reaction. So we use symbols to represent chemical reactions. Now, a typical chemical equation has about 5 components. The first component are what we call reactants. Reactants are substances that undergo the chemical reaction. We usually write these on the left-hand side of the equation. We then have products. Products are the new substances that are formed after a chemical reaction has taken place. Products are usually written on the right-hand side of an equation. We then have an arrow. An arrow is usually put in between the first 2 components. The arrow points from the reactants to the products. And what an arrow does is simply to indicate the direction of the reaction. Let's now look at the other 2 components of a chemical equation. We have state symbols next. And what state symbols do is to show the physical state of matter of both reactants and products. Learners should know that if you do not put these in an equation, then you end up losing half a mark. So we usually use the following common state symbols. We use S, bracketed of course, to mean that your reactant or product is a solid. L stands for liquid, and then we have G standing for gas, and aqueous, AQ, to stand for soluble salts in solutions where the solvent is water. I know at Form 2 level, most of our learners confuse when to use AQ, because at that point when we are learning about chemical equations, we have not done the topic of salts. So to know which salts are soluble in water and which ones are not may be a little bit tricky, but the moment we go through salts as a topic, then this becomes very easy to navigate. We finally have coefficients as the last component of a chemical equation. So what are coefficients? These are numbers that are placed, take note, they are placed in front of the chemical formula to balance the equation. Learners, I want you to take note, these coefficients are not placed after, neither do we place them in the middle of a chemical formula. They have to be in front of the formula. Now, the coefficients represent the relative number of moles of each substance that is involved in the reaction. At this point, let's now move on to learn how to count the number of atoms of different elements making up a compound. To learn how to count the number of atoms of different elements that make up a compound, let us consider the following 6 chemical formulae, beginning with H2O. So here we have got 2 elements. There is hydrogen and oxygen. Now, this number or this digit 2 will only affect the symbol before it, the symbol on its left hand side. So in this case, hydrogen atoms are 2, but the 2 will not affect oxygen, and therefore we only have 1 oxygen atom. Let's see what happens next. We have H2O2. This 2 is going to affect the hydrogen and not oxygen. Then this other 2 will only affect oxygen and not hydrogen. So in our second formula, hydrogens are 2 and oxygens are also 2. Let's move on to the third one, where we have 3 into H2O. Now, we've agreed that this 2 here only affects hydrogen, but the coefficient before the formula, that is our number 3 or our digit 3, will affect both the symbols that we have here. So hydrogens, we have 2 that have to be multiplied by 3. That gives a total of 6. And for oxygen, we are going to have 3 atoms of the same. This 3 affects even oxygen. Moving on to the fourth one, we have sodium here now. We have phosphorus and we have oxygen. For sodium, we've agreed the 3 here will affect it, so we have 3 atoms. Phosphorus is 1 and oxygens are 4. Learners, let's now have a look at effects of a bracket by looking at the 5th formula that we have here. So the elements present in our formula are 4. We have nitrogen, we have hydrogen, we have phosphorus, and there is oxygen. Now what happens here is the digit 3, which is outside the bracket, affects all the elements that are inside. So in this case, our nitrogen atoms are 3, because this 3 here affects it. Hydrogens will be 4 multiplied by 3. That gives 12. Phosphorus remains 1 and oxygens are 4. We finally look at the effect of a coefficient before the bracket. So here also we have 4 atoms of different elements. We have nitrogen, we have hydrogen, we still have phosphorus and oxygen. Nitrogens here affected by the 3 on the right of the bracket and a 4 before the bracket. That would give us a total of 12 nitrogen atoms. 3 times 4. For hydrogen, we will have 12 multiplied by 4, and that gives a total of 48 hydrogen atoms. 3 by 4 is 12, by another 4, 48. Phosphorus remains 1 and oxygens remain 4. Dear learner, we have learned how to count number of atoms of different elements that make up a compound. This skill will be very, very key in balancing chemical equations. So let us now proceed to the main point of making this video, and that is balancing chemical equations. We will start with meaning of balancing a chemical equation, and this simply means the process of we adjust only the coefficients of the reactants and products in an equation. Why we do so is to ensure that the law of conservation of mass is satisfied. Now, the law of conservation of mass states that matter cannot be destroyed or created in a chemical reaction, but can only be changed from one form to another. So that means that the total mass of the reactants must be equal to the total mass of the product. In short, we will ensure that the number of atoms of each kind are the same in number on the product side and on the reactant side. With that, let's now move on to take some 4 examples which shall explain how the balancing of chemical equations are done, and our examples are going to be increasing in complexity as we proceed from example 1 to example 4. So in example 1, we have silver in solid state reacting with hydrogen sulfide gas to give silver sulfide and hydrogen gas. Let us see whether our equation is balanced by counting the number of atoms of each kind on the left-hand side and on the right-hand side. Let's begin with the reactant side. So we have silver, we have hydrogen and sulfur. Having learned how to count the number of atoms of each kind, let's go ahead and do so. This side, silver is only 1, hydrogens are 2, sulfur is 1. Let's move to the product side. Again, we have silver, we have hydrogen, and we have sulfur. On counting, we realize silver are 2, hydrogen are also 2, and sulfur is 1. Now when we compare our numbers, you realize sulfur is balanced. We also realize that hydrogens are balanced. The only issue here is silver. So I have 2 on the right, only 1 on the left. So how do I make silver to be 2? I simply put a coefficient 2 here. It has to be in front of the symbol silver. And when I do so, I have now increased the number from 1 to 2. On rechecking, I now realize all my atoms are equal. So the equation is balanced. Let's have a look at example 2. In example 2, I have potassium hydroxide, aqueous, reacting with carbon dioxide gas to give potassium carbonate and water. Let's see how to balance this equation, but first, let us see how many atoms of each kind we have on both sides. Beginning with the reactant side. We have potassium, we have oxygen, we have hydrogen, and we have carbon. On counting, I realize potassium I have 1 only here, oxygens I have 1 here, and 2 on carbon dioxide, making a total of 3. Hydrogens I have 1, carbon also 1. Moving to the product side, I still have potassium, oxygen, hydrogen, and carbon. Let's see how many. Potassiums are now 2. Oxygen, I have 3 plus 1 here, giving a total of 4. Hydrogens are 2. Carbon is 1. From here, I realize that carbon is already balanced. The other 3 are not balanced. So when I look at this equation, I realize that I can easily balance it by looking at potassium or hydrogen. They look simpler because if you look at oxygen, it appears in more than one substance, both on the left and on the right. So we shall approach this equation from the potassium side because it makes the work easy. Potassium appears to be simple because it appears on only one substance on the reactants and one substance on the product. So I want to make potassium 2 on the left so that I equate it to the ones I have on the right. Let me put a 2 on my potassium hydroxide. When I do this, my potassium atoms are now 2, but this affects oxygen as well. Instead of 3 on the left, there'll now be 2 plus 2, which will be 4. And again, if you look at hydrogen, the 2 here has affected it. I'll now have 2 instead of 1. And you can't believe this? By putting a 2 on my potassium hydroxide, all my other atoms are now balanced. 2 for potassium, 4 for oxygen, 2 for hydrogen, and carbon remains 1. Equation balanced. Let's move to example 3. In example 3, I'm reacting ion 3 chloride in solution with aqueous sodium hydroxide to give ion 3 hydroxide as a precipitate solid and sodium chloride in solution. Let's see how to balance this. This time round, I have 5 different types of atoms on both sides. Ion is on the reactant side. I have chlorine as well on the reactant side. Sodium also appears. Then I have oxygen appearing as well. And lastly, I have hydrogen. Let us count how many of each kind we have. Ion is only 1. Moving to chlorine, I have 3. Sodium is 1. Oxygen, I can see 1. Hydrogen as well, 1. Moving to the reactant side, I still have ion. There is chlorine. There is sodium. There is oxygen as well and hydrogen. Let's see how many we have. On the right, ion is still 1. Chlorine is 1 now. Sodium, I can see 1. Oxygens, the 3 here will affect it, so I have 3. And hydrogens are also 3. So here, I can see only ion is balanced and sodium. So sodium is balanced, ion is balanced. The other 3 are not. So, looking at the equation carefully, I realize that oxygen and hydrogen are affected by the bracket. So I will not approach my equation from a complicated front. The bracket complicates oxygen and hydrogen. So what I do is to approach this equation from the chlorine side because it appears simpler. So what do? I have 3 chlorine on the left. I want to make them 3 on the right by putting a 3 here. By doing so, my chlorines are now 3, and I've also affected sodium. Instead of 1, I now have 3. Now, once I do this, I realize I have created an imbalance on sodium on the left. So I'll also need to make my sodiums to be 3 on the left. So what do? I put a 3 here. so that my sodiums become 3 in an effort to balance them with the ones I have on the right. But when I do this, I realize I affect sodium, I affect oxygen, which now becomes 3, and I affect hydrogen, which also becomes 3. And by doing so, looking at my number of atoms, I realize I now have equal numbers on the left and on the right. Conclusion, equation balanced. Let's finally have a look at example 4. And dear learner, I believe these 4 examples are going to play a big role in helping you balance even the most complicated of chemical equations. Now to our 4th example, ammonia gas reducing copper 2 oxide solid to copper, nitrogen gas, and some water or steam. As usual, we begin balancing by counting the number of atoms of each kind on the left and on the right. So on the left we have nitrogen, we have hydrogen, we have copper and oxygen. Let's count. Nitrogen 1, hydrogen 3, copper 1, oxygen 1. Let's see what happens on the right. Nitrogen, hydrogen, copper, and oxygen. Counting, nitrogens are 2, hydrogens are 2, copper 1, oxygen 1. Now, copper and oxygen appear to be balanced, but there is an issue with hydrogen and nitrogen. Now, looking at this equation, you realize nitrogen stands alone. So we are not going to approach the equation from nitrogen. Let us now use hydrogen to try to balance, because nitrogen is standing alone on our right hand side. So here, I want to balance 3 and 2. And the easiest thing to do is to raise the numbers to 6. So I'll do 2 by 3 for my hydrogen, by multiplying by 3 to give me a 6. So let me put a 3 on my hydrogen or on my water in an attempt to make the hydrogens 6. So when I put a 3 here, hydrogens are 6, yes, but you realize the effect of 3 on oxygen, instead of 1, they'll now be 3. Moving to the left, I again need 6 on my hydrogen, so I'll multiply this by 2 to give a 6. So that means I'll put a 2 on ammonia. When I do so, hydrogens are 6, yes, but I've also affected nitrogen. Instead of the original 1, they are now 2. Now, so far, nitrogen balanced 2, 2, hydrogen balanced 6, 6, copper balanced 1, 1. But there is still an issue on oxygen. 1 on the left, 3 on the right. So what do? I'll be forced to put a 3 before copper 2 oxide in an effort to obtain 3 on oxygen. And surely I get 3 oxygens. But you realize that my copper has now moved from 1 to 3. So again, by putting a 3 here, I'm creating an imbalance on copper atoms as well. So now I have 3 on the left, but I still have 1 on the right. So how do I make these to be 3? By putting a 3 on copper. Then that gives me a finally balanced equation. Quite easy. And on that note, I want to ask our learners to practice with more complicated equations. We are through with this video where we have taken you through balancing chemical equations. Thank you for your time, and kindly keep it right here for more insightful reviews.